INSEE is a proud member of the Siam City Cement Group Public Limited, a leading cement manufacturer in Southeast Asia. The Siam City Cement Group provides world-class construction materials to a host of countries around the world. This includes Cambodia, Bangladesh, Vietnam, Thailand, Indonesia and Sri Lanka. With a plethora of landmarks and buildings that define the skylines of these countries, the Siam Cement Group pledges to be a role model in corporate governance and sustainable development. INSEE Cement, Sri Lanka's premier cement manufacturer, is the brand behind our country's leading cement products and the driving force behind making Sri Lanka more sustainable. With a reputation built on outstanding performance in the quality of our products, unparalleled customer service, the dedication of our employees, our respect for the communities in which we operate, and our ambition to set the standards for the industry of tomorrow, we have contributed to the growth of Sri Lanka with iconic developments across the island. Just to name a few: the Lotus Tower, Altea Residencies, the Colombo South Harbour, Southern Expressway, Mattala Airport, the Kalladi Bridge, the Kotalavala Defence University, Mahinda Rajapaksa International Cricket Stadium. INSEE has cemented its position as the most preferred local manufacturer of cement in Sri Lanka, with its widespread distribution network comprised of over 7,000 dealers in retail segment located island-wide. Today, we have 2 plants in Puttalam and Galle and 2 terminals in Galle and Colombo. INSEE's Sunstar brand is Sri Lanka's first cement product to be awarded the Green Labelling certification by the Green Building Council and was the first blended cement to launch in Sri Lanka. INSEE has a wide portfolio of cements and services to suit all your construction needs. The most popular among them: INSEE Sunstar, INSEE Mahavalley Marine Plus, INSEE Extra for mass pouring concrete, INSEE Rapid Flow Plus, INSEE EcoCycle, INSEE Concrete, Convert by INSEE, state-of-the-art innovation and development facility. Having been a part of Sri Lanka for almost a decade, we will continue to build on our long heritage of shared loyalty, creating trusting relationships with our business partners, people and community, and delivering our promise of building the nation.
Good evening, ladies and gentlemen. INSEE Eye-to-Eye Knowledge Sharing Webinar Session for April 2021. May I welcome all of you on behalf of the INSEE Cement Management to the INSEE Eye-to-Eye Innovation to Industry, INSEE Eye-to-Eye Knowledge Sharing Webinar Session for the month of April 2021. Today, we conduct the 10th webinar session, which was organized by INSEE Innovation to Industry Collaboration Space. INSEE Eye-to-Eye Collaboration Space was organizing this webinar session for the 10th time. And I think knowledge sharing sessions, this is the 25th knowledge sharing session. We, considering the epidemic situation in the global context, as we cannot meet physically, we innovatively thought to introduce a webinar session to make sure that the fraternity is getting the correct knowledge at the correct time. So for today's session, we are very glad and we are honored to have a well-known and a well-reputed resource personality, Dr. David Lowe, Senior Lecturer, School of Engineering, Melbourne City Campus, RMIT University. Dr. David Lowe, thank you very much for accepting our invitation and stepping in front to share your knowledge, experience, and exposure with the engineering fraternity, specifically in Sri Lanka. So this lecture will take a closer look at why corrosion is still one of the biggest durability issues for reinforced concrete structures and how the industry is addressing such challenges through rehabilitation and corrosion control techniques. So today's session will be on durability, corrosion, and rehabilitation of reinforced concrete. So INSEE Eye-to-Eye Collaboration Space, again, welcoming Dr. David Lowe. May I invite Mr. Jan Koenig, Executive Vice President and Commercial Director, Marketing, Sales and Innovation of INSEE Cement, to welcome the gathering. Jan, over to you.
Thank you, Dishan. Very warm welcome to everyone joining the 25th knowledge sharing session from INSEE Eye-to-Eye Collaboration Space. I think we can be really proud that now since over 2 years we are doing these sessions, and with very positive feedback. So a little jubilee as the 25th session and the 10th webinar session. I sincerely hope that once the COVID is over, we can meet all in person again, and have a little cake and celebrate the 25th session as well. Very warm welcome again to the engineers, influencers, specifiers, builders, all of you joining today. And for sure, a very warm welcome also to Dr. David Law. Thank you very much for serving today's session. Very much appreciate the time you're spending with us all today, and for sure that you share your knowledge on this important topic, which is also important for the Sri Lankan context, where we have acid in the air, salty air, a lot of water, and with that also corrosion happening. And definitely it's critical and very important to know for all of us, not only what tests we can do, what calculations we can have to avoid the corrosion happening, what is the thickness of the cover which we need for the reinforcement, so that in the end the corrosion is not happening, and for sure the cost involved for all of that. I think I had a quick sneak preview at your presentation. I'm really looking forward at all of this. It will be technical, but I'm sure it will be very, very interesting for all of us. I would like that you also, from the background on the civil side as well, aside of your research elements, share a little bit on the differences between ordinary Portland cement and more modern cements, whether it's blended hydraulic cement or composite cement, whether it's versus the American or the British standard, and how all of that and the usage of modern cements can also support that the corrosion is not happening or less happening. So with that, I wish all of us really a fantastic 25th overall knowledge sharing session and the 10th webinar session. And I'll hand over to you, Dishan, again, and let's have a good session. Please be active in the Q&A as well, as always. And we are also recording this session again so that we can share it later with you via our digital channels. Thank you very much. Over to you, Dishan.
Thank you very much, Jan. Jan is the Executive Vice President and Commercial Director, Marketing, Sales and Innovation for INSI Cement. Thank you very much, not only for the kind words, but also for the concept behind this mission, while we being innovative to make sure that even at COVID situation, COVID period, that we make sure that the eye-to-eye innovation to industry collaboration space of INSI Cement to ensure that they share the knowledge with the fraternity. So today, as you said, is the 25th jubilee, special jubilee, the knowledge sharing session. It is not that easy to find 25 resource personalities. It is not that easy to gather the fraternity 25 times. It is not that easy to share good knowledge, appropriate knowledge, relevant knowledge to the industry for 25 times. So I think that is a small or important element to celebrate. So let me remind you Dr. David, now today at this moment in Sri Lanka, the time is 5:45, but for Dr. David, it's late night. So I take this opportunity to thank Dr. David specifically for joining with us at this time to share your knowledge and experience with us on durability, corrosion and rehabilitation of reinforced concrete structures. Ladies and gentlemen, you have the Q&A forum at the end of Dr. David Lowe's presentation. But before that, while the presentation is ongoing, if you have any query, in this Zoom application, you have the Q&A column. You can put your query in that particular column. So that will facilitate, that will be convenient for us to pick up your important questions and forward it to Dr. David Lowe. And I will take this opportunity to present the profile of today's resource person, Dr. David Lowe. Dr. David Lowe is a senior lecturer at RMIT University, Melbourne, Australia. He has published over 75 journal papers and is presently a member of the RILEM Committee on Characteristics of the Steel-Concrete Interface and their effect on initiation of chloride-induced reinforcement corrosion. He has previously been a lecturer at Heriot-Watt University in Edinburgh and worked for both Monsell and Taywood Engineering in the UK as a senior engineer in their materials divisions. His principal research interests are the corrosion and durability of structures. The presentation will cover the durability, corrosion, and rehabilitation of reinforced concrete structures. This will include an introduction to corrosion mechanisms and methods on monitoring and current research area on the residual protection of impressed current cathodic protection of wharf structures in Australia. Let me welcome Dr. David Lowe, and let me invite Dr. David Lowe to carry out the presentation. Sir, over to you.
Thank you very much for that introduction and also for the invitation to speak. So I'm fairly familiar with Sri Lanka, having been a few times for the cricket. And we have a number of Sri Lankan research students at the moment. So I have 3 Sri Lankan research students who are working for me at RMIT at the moment as well. So it's very good to be able to speak to you in Sri Lanka. So what I will be talking about is some of my experiences. So I'm just trying to see where the share button is. Share screen, there we go. Yeah, there we go. Yes. So what I was going to talk about today is sort of the work that I've done, both in industry, where I've sort of said worked in the UK and in Australia for a number of companies, looking at durability and corrosion issues for reinforcing concrete primarily, and that's what I'll talk about today. So I'll be talking a little bit about some of my experiences on those structures and the inspection of those structures. What is corrosion and what are the factors that affect it? And also a little bit about the research that we've been doing, and in particular at the end, focusing on a current project where we're doing a lot of work at looking at cathodic protection systems, many of which are now coming towards the end of their design lives, having started in the sort of 80s and 90s, and indeed really why I'm working this area, being more of an electrochemist, looking at the corrosion and durability, and also the design and installation of ICCP systems sort of in the early 90s in the UK. So just to give people a little bit of an idea about RMIT University, we're based down in Melbourne, which is down in Australia, though I'm actually British and from the UK, and have worked at Heriot-Watt in Edinburgh was my last university, and before that at Liverpool University. RMIT has 3 campuses in Melbourne. We've got the main city campus is where our offices and classes are held, and we then have Bundoora campus, which is where our laboratories are held, and then we have another campus, the Brunswick campus, which is more for the arts and textiles area. We also have campuses in Vietnam and Barcelona, where we also done some collaborative research with them. We have about 84,000 students including 12,000 postgraduate in both research and taught. We had 12,000 international students. I'm not quite sure, given the current situation, what the numbers are actually like after this year's intake, but hopefully we will be back at those numbers relatively soon. And the majority of these students are based on our city campus, which accounts for about 45,000 of the students. And within civil engineering, we have about 300 to 350 in each of our 4 years of our courses. Within the School of Engineering itself, which goes across a large number of the different engineering profiles, we had 289, so nearly 300 academic staff, produce around 600 Q1 publications a year, have just under 5,000 undergraduates, and about 1,279, so the last time we looked there, on coursework, and sort of 580 HDR students, the majority of these in PhDs. And in civil, we have probably around 150 PhD and Masters by Research students within that. And I have, I think, 11 currently working with me, and a couple in the process of writing up at the moment. So these are the academic disciplines within engineering, and I'm particularly in that civil and infrastructure engineering area, but do some collaborative work, particularly with the chemical and environmental engineering group. Within sort of the expertise that we sort of deal with at RMIT, we look at sort of pretty much all types of structures. We're also very interested in power and energy, transport networks, and mining structures. And in particular, I would say sort of buildings, bridges, mining, and road are the main ones that I would deal with within my research, from the area of durability, corrosion, and long-term performance. So what sort of going to focus on is our corrosion and durability research at RMIT. I'll start off talking a little bit about the corrosion processes and how corrosion is initiated, particularly focusing on chloride-induced corrosion. Then do a little bit looking at some of the measurement techniques that we have, and testing, in particular things like linear polarization measurements, laser scanning. We'll then talk a little bit more about corrosion and bond as well. And then I'll sort of move on to focus about electrochemical protection with cathodic protection. So why are we particularly interested in corrosion? Well, in the extreme cases, we can have major failures. And you may remember the Genoa Bridge that collapsed a couple of years ago, when there was a number of fatalities. And there have been other collapses, Minneapolis Bridge about 10 years earlier. And we have sort of issues with the Forth Road Bridge, where I used to be in Edinburgh. Sort of major corrosion of the suspension cables led to having to construct a new bridge, which was opened in 2017, because of the potential disruption if that bridge was shut and there was perhaps a 50-mile detour required because of its shut. And in Melbourne, we're currently building a lot of new train lines, and part of this is based on the premise that it's very difficult to actually get into the tunnels and do the repairs and shut down the system of the existing single tunnel that we have actually underground running through Melbourne is a major cause of concern within that. So we're looking at this because we need to maintain this infrastructure. And if we have failures in this infrastructure, it's going to be a major cost to the repair, but also the disruption. So even if there are no fatalities, and the illustration there was a collapse overnight due to corrosion in the bridge, which had been caused by de-icing salts being applied on the surface, not an issue that you would have in Sri Lanka, but obviously in Sri Lanka, there are other issues with regard to it being an island and much of the infrastructure built in a marine environment where you've got the chlorides that can get in and cause deterioration. And obviously higher temperatures, high humidities can also drive that corrosion even faster. And it costs a lot of money. So there was a survey going back in the USA, 1982, that identified 15% of all the bridges at that time, which was over 500,000, were actually structurally deficient. And the estimated repair costs were 8.3 billion a year, equivalent to 0.1 GDP. And that hasn't really changed much in the last 30 years. There was recently a study done in Sweden, and that estimated the repair costs were 0.08 GDP. So as you can see, those repair costs are staying fairly constant, but things have the potential to actually get considerably worse. And that is, at the moment, we have approximately 40% of the bridges are over 50 years old, that area where we might expect that durability to be a problem. By 2050, that will have risen to 75%. So that is going to be an awful lot of money that is going to have to be spent. And it's estimated that if we extrapolate this to all structures, we're looking around $300 billion annually in the US. And in most developed countries, I expect this to be around 3 to 5% of GDP for all those structures that are there. And again, here is another example of where we've got durability failure of steel pipes. So these are water pipes in the main. In the US, it's expected that that might be 1 trillion over the next 25 years. In Australia, we have estimates of just under 125 million over that same period. And these leaks, which might seem small leaks at the start, can progress to what we see in the image below if those leaks get out of control. And with a lot of this durability, it's very difficult to actually see what's happening because it's steel that may be buried, it's steel that's within concrete. How are you going to actually be able to test this? And how can you repair it? And how as well can you design for it? And indeed, the selection of your concrete and your concrete mixes and the sort of cover depths from those is very important in how you're going to hopefully try and prevent these failures. This is the sort of thing that you see on the old structures, and just got some examples here of what happens when you have corrosion of your reinforcement. And so the bottom one, obviously the top one here is a marine structure. The bottom one is actually also on a bridge where you've got corrosion. This is actually a bridge, but in Central Europe, and that's due to de-icing salts again. The bottom one is actually due to water leaks that are coming through, and they are then initiating the corrosion sort of inside the concrete that are there. So how does chloride get into our concrete? What happens? Well, our chloride may come from our de-icing salt or from the seawater, and what it will do is it will slowly diffuse into our concrete. That is, it will come into the pore water that we have within our concrete, and it will diffuse under that concentration gradient of chloride ions until it reaches the steel bar. And once it reaches your steel bar, you will actually get corrosion initiated. And thus, the protection that you've got is your concrete. You've got the distance, the cover depth, you've got the density or the compaction, the porosity that you've got in that matrix as well, because it will diffuse through the interconnected pores and the pore water. So those are how you can try and sort of design out chloride attack. But when the chloride ions come in, they will then reach a concentration at this steel rebar that will initiate corrosion. And this is what happens. This is, you set up an electrochemical cell. You have an anode, and that's where your iron dissolves from your steel. So your Fe goes to your Fe2 plus, and you have 4 electrons generated. And these move along the rebar to an area on the bar that we would term the cathode. And here that reacts with water and oxygen to form hydroxyl ions. And thus we need both water and we need oxygen at the bar for that reaction to occur. And then these hydroxyl ions will be transported through and generate and create the full circuit. They will meet the ions that have dissolved, and we get iron hydroxide forms. This then changes into the rust, and you see that typical orange rust that you see on the surface. This occupies a larger volume than the steel, because the steel is now combined with our oxygens or our hydroxyls, and so it puts a stress on the inside of the concrete, and so the concrete will collapse. And you will get cracks, you will get spalls, and you will get failure of your concrete. And that is how our steel corrosion is initiated when we have our chlorides. And why does it happen? Well, this is a pour bay diagram. And when we have our normal concrete and our pH, we are in sort of this pH 10 to 12 zone, 13, and that is where we get passivity. That is, we will have an iron oxide film formed on the surface of our steel, and it will protect our steel because of the pH that we're at. However, if we have a drop in our pH, or we have chloride ions coming into the system, we move from a passive region into an actively corroding region. And so we move from this passive zone into this corroding zone. And so that is why we start to get corrosion. And so thus, as the chloride ions increase, or the pH drops, which happens when we have carbonation attack, and that neutralizes our pH in the concrete, we move into our corroding area. And that's where our Fe wants to move to our Fe2 plus. And so that is a problem that we've got. And while I'm here, just to mention, you've got this area of immunity. And you can see these are at very low potentials. So when we have a steel potential and it's passive, it's generally in the region, say, minus 100, 200 millivolts. When we move into the active corroding region, we're moving down into lower millivolts, which are generally 300, 400, 500 millivolts. But if we get to very low potentials, we actually get immunity. And this is what we do with cathodic protection that I'll come back to at the end. And these are what the problem is, that when we have chloride attack, we get what we would call pitting corrosion. That is, it corrodes at very small specific points on our steel. And these pits mean we can lose a lot of section of our steel. This is uniform corrosion. This is what we tend to get if we have carbonation attack. The same amount of steel has been lost in both of those bars. However, you can see you've lost a lot more cross-section in this bar, which tends to come from chloride attack, than you would do from carbonation attack. And it's that steel section that provides the structural support. And so you're far more likely to have those failures with chloride attack than perhaps you would see with carbonation attack. And when you've got this corrosion, these cracks form. And so if you have beams, the cracks tend to come out at the corners, and you have the concrete falls off, you have spalls, and you get exposure of your steel, which can then corrode faster. When you've got slabs, it can quite often be that you'll see the bars will connect up with those cracks, and you get larger, flatter areas of spalls coming off when you have slabs, and that might be in the soffit, or it might be sort of when you've got sort of the slab on a bridge deck coming off with them. But I said it's this pitting corrosion that is a real problem when you've got chloride-induced corrosion. So how do we go about assessing this? How do we know what's happening within our concrete if we can't see what's happening at our concrete, at our steel, because of the concrete? Well, we can look at what's called half-cell potentials. That is, we can look at what that steel potential is that we talked about in the Poor-Bay diagram. And from that, it will give us an idea of whether it's passive or whether it's corroding. We can do what are called linear polarization resistance corrosion rate measurements. We can get an instantaneous rate of corrosion. We can also look at resistivity. What's the resistivity of our concrete? If we've got a lot of chloride ions in there, the resistivity will drop. If it's very damp, if it's moist, the resistivity will drop. And we can also look at what's happening. What is the chloride diffusion coefficient? What's the rate that our chlorides are coming in through our concrete? And one of the things that we do when we have a mixed design, we want to have a chloride diffusion coefficient for that concrete that is very low, which means that if we have a set thickness with that chloride diffusion coefficient, the chloride ions are not going to reach our steel within our design line. And to do that, we can use some predictive modeling to see whether it's going to reach our steel, and we can design to try and ensure it doesn't reach our steel. But sometimes it does, particularly as structures age or the exposure environment is actually more aggressive than we thought, or it can even change. And so we need to think about how we're going to do repair and maintenance. How are we going to repair and maintain these structures? Well, so for those techniques, the most common technique is to do a half-cell survey. And to do this, we would have a half cell. That is a standard electrode that we are going to use to measure the condition of the steel. Generally, when we're doing it on the surface, like these guys here, we would use a copper sulfate electrode because it's pretty robust, and so it can take the knocks that might come with it, and it will give you a pretty good idea of what's going on, perhaps plus or minus 5 millivolts in inaccuracy. If we want to sort of monitor this over a long period, though, we may well want to actually install an electrode in the concrete and see what's going to happen over a number of years, perhaps 20, 30 years even. And for this, we can use things like silver chloride or manganese oxide electrodes that are more stable and will last longer if we put them inside our concrete, whereas our copper sulfate will not last that long because it will dry out if we leave it, try to install it inside our concrete. To do these surveys, we need to have a connection to the steel. So that may well mean that we need to break out with a drill or a hammer, or we may need to the steel and make a connection to that. We then need to set up a grid on the surface so we can record it at set points. And these, we can see the people are putting them on at these set points on the grid, so we can build up a contour map. And we take points along there. You can get potential reels, but it needs a fairly flat surface to be able to roll it along. And you also need to use a high impedance voltmeter, or you can get some of these automated devices, such as the one at the top, where it just records each time it's put on the surface. At the bottom, this was some of my research students, and so they would read out the number and someone would actually write it down to be able to produce that information. And then we get these contour maps. And you can see here, we've got these green zones where the potentials are more likely to be in the passive range. And then we've got these red and yellow zones where they're more likely to be in the active range. And thus we can see we've probably got the green is the cathode, the red and the yellow are where we've got anodes. And if we can't see any cracks or rust yet, we're suspicious that we actually have got corrosion going on. And so these are the areas that we might want to look at in more detail to measure the corrosion rates and see how fast that steel is actually corroding and whether we can do anything about it. And we can look at these with a set of criteria that relate the steel potential to the likelihood of corrosion that are called the Van der Veer criteria. We can look at the shape of these corrosion pots. If they're all of the same sort of potential, then it's likely there's no corrosion occurring. But when we've got these big like contours that go from green to red and yellow very close together, then it probably does mean that we've got corrosion there. And we're also looking at those environmental conditions. In Australia, for example, if you're in at the end of summer when it's been very dry, there'll probably be no corrosion because you're in a situation where there's no moisture or little moisture. Equally, if it gets in the monsoon season, there'll probably be no corrosion because there's no oxygen present. So you need to think about, well, what's the environmental condition when I'm taking these readings? And so occasionally we have specimens up in sort of tropical Queensland. We went up there once a couple of days after torrential rain. And of course, we saw no corrosion on the specimens, even though we knew that they would corrode most of the year. But it was just the timing with it. So you do need to be careful about the environmental conditions, that they are not going to be atypical of what's happening. And it shows you no corrosion, even though most of the time they will be corroding. So that is how we can get those steel potentials. The linear polarization resistance is a method of actually determining the corrosion rate. And this will look at changing the potential and measuring the current when you change the potential. You can have a 3-electrode system, which is the most common, and I'll talk about. You can also have a guard ring, which is the bottom one, which has 2 extra electrodes to see that the current that the potential that you're changing is not going outside a certain area, so you know the area of steel that you're dealing with. But in general, sort of these days, a 3-electrode system is probably more normal, but you can use these guard ring systems to try and ensure that you've got a set area of steel that you're measuring. This then is how a 3-electrode system works. What you've got is you've got your reference electrode. In this case, we've got silver chloride, but you can use a copper sulfate. We've got the steel, which is connected, and that's termed the working electrode, because that is the one that the work is done on. And we then have an auxiliary electrode, and that is what will apply the perturbation to move the steel potential. That will apply a small current that will shift the steel potential by a set amount. And we then will measure the current response as that returns to its equilibrium potential. For the auxiliary electrode, we need a conductive foam to get a good contact, and we will generally use a brass plate that corrodes a little less likely and will be more long-lived within it, but you could use any metal there if you wanted to. And we're able to interpret this because we can represent the corrosion in concrete by this simple circuit. This resistor refers to the concrete, and it's called the solution resistance. That's the resistance that you get through your concrete. And then your steel bar has a capacitance and it has a resistance. This is the double layer capacitance. That's the Fe2 plus and the Cl minus that are opposite each other on the bar. And that's the capacitance that you need to fill up. And then you've also got your resistance. That's the charge transfer resistance. That's related to the corrosion of the steel. And so what you can do is you can actually measure this. You measure this with your LPR because it will measure the 2 resistances added together. But because you have a capacitance here, if you use an AC impedance measurement, you can short that out. And so you will just measure your solution resistance because it will go along here and there's no capacitance, and it will just go along this side of the circuit and not go through the RCT resistor. So you can measure your RS and you can measure your RS and your RCT using this LPR technique. And here you can see me in the days when I was working for ACOM in Australia, undertaking a sort of corrosion rate measurement. So what we did, we've sort of done a cover survey, we've made a connection to the steel, we've done a half cell survey and identified those negative points, and now we're going to do a corrosion rate measurement on that. At that point, you can see the tide comes in. It doesn't actually come up quite that high, but it's in a very aggressive environment because you will get the moisture, you'll get some spray and some splash, but it'll also be drawn up by capillary action. So this is a very aggressive location. And this is what will happen. So we're going along and the steel is sitting happily at its normal steel potential. And then you change the potential up and you change the potential down by applying that current from the auxiliary electrode. And over time, you'll get a charging up of that double layer capacitance. And when that's charged up over time, you will get, and it will sort of reach an equilibrium point. And so you've got your delta I, the current that relates to what is your solution resistance and your charge transfer resistance. You know your delta I and you know your delta E, and we know that V equals IR. So we can calculate our polarization resistance, delta E over delta I. And we also know that we can calculate our solution resistance separately. So if we subtract our solution resistance from our polarization resistance, we will be left with our RCT, the resistance that relates to our corrosion at the moment we retook it. We then can correlate that with our corrosion rate using a constant, which is the Tafel constant. And if we then divide that instantaneous corrosion rate by the area of bar underneath it, and that's why you sometimes use that guard ring, we can then calculate what is our corrosion current density. And from our corrosion current density, we can then use the Faraday equation to calculate how much section loss we're getting in our steel per year. And thus we can see how much steel we're actually losing per year. And so we can see how long before we will actually get structural concerns about that steel that's going through it. And that, I said, is the Faraday equation. We've got the atomic rate of iron, the density of steel. We know it's 2 plus because it's Fe to Fe2 plus, and we've got our Faraday constant. And these are the sorts of things that we see when we actually go and measure this on structures. And we've done a lot of work with this. And so we get our corrosion rate, and this is then sort of going to be sort of what this equates to in sort of our microns sort of that are being lost. Actually, that shouldn't be milliamps, but so we can sort of then see that we can get our maximum corrosion rates, our highest in that splash zone. In carbonated, they're down at about 2. We get a lot higher in the laboratory. And when we then convert those to our mean corrosion rates, if we multiply that by a number which is approximately 10 that comes out of that Faraday equation, that will tell us how many microns of steel we lose per year. So typically, we can be losing around 20 microns of steel a year in our splash zone. In our carbonated concrete, it might be down at only, say, 1 sort of micron a year to 5 micron a year. So that's that difference between our pitting and our uniform as well. You can see that chloride corrosion goes a lot faster than our carbonated corrosion. I can say that on site, I've actually had values up here that not 20, but actually 80 microns a year or 90 microns a year. We have seen on occasions, but generally they're in these zones for the typical site data. So this is how we can sort of go through and estimate sort of our sort of like section losses, and our corrosion rate can then be correlated to how much we lose over a longer period of time. So there are various ways that we can then go forward to sort of estimate the service life of our structure based on the information that we've got out of that data that we get from our corrosion rates. And thus, in the end, we can get actually to our residual section, which is the main thing we're interested in. And so this is the residual section of our steel that is related to our penetration depth. So we can get what we say is our time to cracking, and we can get, most importantly, that time to failure that we can try and estimate from our corrosion rate measurements. Another interesting technique that we've been using is to look with a laser scanner to try and detect deterioration on a structure. So we had here a block that we put in the laboratory. We're actually corroding this by applying a current to make it corrode faster and spraying it. And we are monitoring over time using a terrestrial laser scanner. We also went down and actually scanned a seawall as well to see what was happening on a real structure. We did this because obviously we wanted to get the data in a shorter period of time. And this is the seawall that we're scanning again over a period of time. So we did the scanning of this over a 2-year period, but it's still ongoing now actually. So it's been going about 5 years, and we occasionally go down and sort of deal with this. The idea being that if you can scan it, we're getting reasonably close, but you may be able to do these scans from a long way away. So you don't have to go and actually do the visual inspection where you get right up to a structure. You can simply do these scans from a distance away, or even these days use a drone to be able to do these scans. So it can reduce the cost and hopefully increase the accuracy. And so these are some of the data that we had. So we had a set of bars that were in our laboratory specimen, and we put in 5% sodium chloride, and we accelerated our corrosion with a 200 microamps per meter squared. We've got that seawall was 40 years old, and it's got quite bad chloride-induced corrosion in it. And thus, we were able to sort of do a set of scans, and you can see here where we can sort of use the resolution of our laser scanner to actually pick up the crack patterns that we had got on the blocks themselves. And so you can see here, this is what it looked like in the lab, and then this is how we can enhance it using our laser scanner. What we did find is that we needed the cracks to get to about 0.5 millimeters before we could actually really follow them with the laser scanner. This is because the cracks, the laser scanner was getting lost in those very small cracks and not being bounced back accurately enough to be able to see them. But once they got to 0.5, then we could produce these maps that we could see down here. And so this very good way of actually seeing where the cracks are, but we can then actually monitor the crack growth over time using this technique. This was our wall that we saw over time. And what we saw here, this red zone, is it's actually moving out. So the top one is where we were at the start. And then over time, we saw this red zone. And so this is the end of it. And this is what it looked like. And at the end, a spall fell off. And so what we were seeing is this concrete was debonding and moving towards us over time. And we had not expected to see that at all when we'd done this scan. We were just thinking we might be able to see cracks appearing. But what we could see is when we started at the beginning of the 2-year period, that was the position. And then after about sort of 9 months, we got to here. And then after about 18 months, 2 years, we got to here. And then about another year or so later, this bit of concrete actually fell off. And this was really good And sort of like for us, that it really showed us that with this technique, you can actually see the rust that's formed pushing off, debonding your concrete. And this is something that we're really interested in and looking as if we can sort of use this technique to really see not before cracks appear, but where we can see delaminated concrete. And of course, so the idea is this is very useful for areas where you can't get to very easily to do that visual inspections. So another sort of thing that we've been looking at is looking about what happens with the corrosion and that bond to the steel. So again, we're very interested in the bond of the steel, because obviously it's that composite action that gives strength to your structure and the capacity remaining. And we're interested in, is there a relationship between crack width and the bond? Can we see that we've got a relationship in crack width and bond? Because if we can monitor the cracks, then we might be able to understand how much bond we're actually losing as well, sort of within. And so we designed a set of specimens where we've got the bond in, we've got a bond breaker here. So when we clamp it down, it's not pressing on the bar. We will have 16 and 12 millimeter bars we looked at. We had stainless steel links to make sure these didn't corrode. We were just trying to corrode the bars. And we looked at a range of cover depths of 1, 2, and 3 times the cover of the bars over a large set of specimens that we've looked at. We would then clean the bars, so we could see how much mass loss as well we were getting out of them. This would then be, again, accelerating the corrosion within the bars, and so we would sort of have these bars wired up, and we would be able to do pull-outs of the bars. We had them with the long bars opposite, so we could fit them in the machine. If we had all 4 bars in, we couldn't fit them in the machine to be able to sort of pull them all out. In this case, we cast them with 3% sodium chloride, and we had wet dry cycles running for 1 day wet, 2 days dry, and we would stop these at specific crack widths to test what the bond was on them. Here you can see sort of the specimens again in a spray cabinet that we were looking at sort of for them. This is how we would do the test. So they're clamped, but we've got that bond breaker here to make sure there's no reaction, and we pull them out in a sort of perpendicular direction, and this shows you sort of the section of some of the bars that we took out. Here, sort of typically after cracking, after bond failure, we get these cracks, and sort of here we have another one where it comes straight out, where we've just got the longitudinal cracking. This was typical for unconfined. This was typical for confined, as you might expect. And these are the sorts of graphs that we got. And what you see, interestingly, is that when you start with corrosion, you actually get a bit of an increase in strength. And that's because that extra corrosion acts as extra ribbing and an anchor into the structure. But then once you get past that, you start to get a deterioration. In some cases, we get a very good relationship, and in others, it was nowhere near as straightforward as to what was happening sort of with those relationships. So as you can see, there is a difference in top and bottom cast bars as well, sort of within that, and that's because the top cast bars perhaps have more space underneath them, so they could certainly increase a lot more in strength, because there's probably, being top cast, there's probably a few more voids in those, and they get filled in by the corrosion product, and so you actually get a bigger enhancement of strength in those before you start to get the failure than you do the bottom bars, where you perhaps can see a little bit of an increase, but not too much before you start to get sort of the failure coming through. You can see here, this was the mean crack width, and this was the maximum crack width. And again, the maximum crack width gave us a better relationship actually than a mean crack width on that deterioration. So there was a suggestion, and this is still again some ongoing research, but simply by being able to monitor and measure those crack widths, we will get an understanding as well as to how we're losing bond from the bars. So the final bit of work I was going to talk to you about is the cathodic protection systems that are used to rehabilitate structures. And this would be, I would say, the most common method of rehabilitating chloride-induced corrosion on structures. There are 3 different types of cathodic protection. There is the impressed current cathodic protection that uses an electrical current to protect them. These are the ones that are most used. These are the ones that have been running now for 30, 40 years. And these are the ones that we've been studying to see, as they're reaching the end of their design lives, are we seeing protection left on the structure by the action of this cathodic protection over that long period of time? Because if it is, it means that those structures will last longer, and so we don't need to reinstall ICCP, and they may well reach their design lives. And trying to understand that in the different locations, the different elements, is very important now. There's a lot of these systems that are at the end of the design lives. You can also have the sacrificial anode systems. That is, you use zinc to protect them. These, of course, are easier to replace because you can just add more zinc and replace the zinc if you need to. but they can have more problems putting in enough protective current to protect your system. And there is a new system, a hybrid CP, that's been coming in the last 5 years or so, that effectively uses impressed current, or applies a current, a very high current for a short period of time to get the steel passivated, but then protects it over the longer term with a sacrificial anode, because once it's passive and you've got that passivation, you've got that residual protection that can just be maintained by your sacrificial anode. And again, trying to understand when you will lose residual protection and how much current you're going to need and how long it lasts and how much residual protection you need will affect how long this hybrid will last and how much zinc you need to protect it, and the zones where you will perhaps need to sort of like not be able to apply hybrid, or whether you can apply it in all locations. And if you are applying it, how often you might need to replace any zinc that you've left to maintain the protection. So this is how the ICCP system works for those who are not familiar with it. What you have is you'll have your reinforcing bar, which is corroding. And what you do is you apply onto the surface an anode. So this could be a ribbon anode, a mesh anode, or even a conductive paint. And then this gets connected. So your anode is connected to your DC rectifier. So you're having a direct current, and your steel is connected to your DC rectifier. And obviously your steel becomes your negative terminal, and your anode is the positive terminal. And this means that your chloride ions are to a degree repelled from your steel, and you're generating hydroxyl ions at the surface. So these are what termed the secondary effects. So what you're doing when you apply it, you're polarizing the steel into that immune area that I talked about at the beginning by sort of reducing the potential to around -11, -100, 1200 millivolts. But you also have this secondary effect. And it's this secondary effects where we think we could get this residual protection and the restoration of passivity, because we've regenerated hydroxyls, we've moved chlorides away, so we can repassivate our steel bar. And if our steel bar is repassivated, then it will be a period of time before corrosion is reinitiated. And it may be the idea behind the hybrid is if you've got some zinc, it will then be able to protect it, and you will not lose that passivation now you've got it for an even longer period of time. But the ICCP said it applies this DC current for a long period of time. These systems, 20, 30, even 40 years now, these are applied for. When you're talking about hybrid, you're probably talking about 6 to 8 weeks, and you're really using sort of large batteries to apply that current. To be successful, you need to repair all of the spools and delaminations to ensure that the current circuit can be set up and those anodes on the surface are sort of work. You also need to make sure that you've got all your steel connected into the system, or it will be corroded if it's not connected into the system. And you also need to make sure that your concrete, the original and the repairs, allow current to flow. So you don't really want polymer modified concrete in there, because that's going to make it a lot more difficult to actually pass the current through your concrete. And of course, your steel needs to be uncoated. So you can't be looking at this if you've got epoxy coated bars in there. So you work out your total steel area, and then you would typically apply between 2 to 20 milliamps. And when I started this in the late 80s, early 90s, we would rack it up to 20 milliamps and leave it there because we weren't sure it was going to work. And what this did was actually generated quite a lot of acid at these anodes. And this at the top, you can see a typical anode ribbon. At the bottom, you can see a typical anode mesh. And so what we found was that we had failures actually of the anodes, which were failing first. We've realized that now, that as soon as you've got this passivity, you want to turn that current down as much as you can, but maintain the protection over time. So platinized titanium here, and I said you can also use a sort of a galvanic coating or a sort of a conductive carbon coating even as a paint to be able to apply it. The mesh, usually you can apply the most current. So if you've got a lot of steel, it'd be mesh. Then you may go down to ribbon, and ribbon obviously can be slotted into quite small areas as well. And then if you don't need too much current, then the conductive paints can work quite well. You need to make sure that you put concrete over all the reinforcement before you apply the anodes, because if the anode touches the steel, the whole system will short out. So you have to be very careful of that. You put in these monitoring electrodes, and then you would then put a surface sort of concrete layer on as well to sort of cover up your anode ribbon and your anode mesh to make sure that that's not on the surface and exposed to the environment, and it's sealed within the system. You have junction boxes, so where you bring all of the connections. So you can see here these sort of ribbons running down here is where you're putting connections on to make sure you've got multiple connections to your anodes, such that if one of those failed, you still maintain the circuit. So you don't just want one or two connections, you want quite a number of connections. You run those back to junction boxes that need to be sealed, because they can quite often be on the bottom of docks, or they can be where you get a lot of splash. You also need to be careful that they can't be vandalized. And you then will run them back to your transformer rectifier units, which again need to be in areas where they can't be vandalized for access. And again, and that is how you set up your systems. So once we've done that, we're now interested, I said, you've put on that protection, but as we're running towards the end of their lifetime, are we getting any residual protection? And anecdotally, there were suggestions that we are. And this has come where we've had fires in the TR units. And so they've been deactivated for a period of time. Sometimes they have to be switched off. Sometimes people actually even forget to switch them back on again. And so you can have periods when they've gone and they haven't had the ICCP actually on the system. But when we've gone back and looked at them, and people have looked at them, they've seen that they are still fulfilling the criteria that they are protected. So what we're interested in is sort of what is happening sort of there. Why are they being protected? How long are they being protected? What are the factors that cause that protection? And if we can quantify this, how long can we say a structure will last after the CP system comes to the end of its useful life? And also, can we then perhaps pulse the systems rather than have them on continually for 40 years? Or, as I've said, you know, how successful will be that hybrid? However, what we've seen is that they're not seen in all structures. And in particular, they're sometimes affected in tidal areas. So we need to understand what these factors are. And to do this, we've set up dual trials. We set up some laboratory trials where we cast specimens, and here we would have a steel bar, an anode mesh, and we would monitor sort of pH, potential, sort of, and humidity within these to see how long they would give residual protection for. These were accelerated systems, so we cast them with 3% and 0.5% salt and a control with 0 salt, and then we would have wet dry cycling to initiate corrosion. We applied CP for a period of time, or that should say 20, not 29. So we had 20, 60, 180, 540 running at 1 to 3 months, so i.e. 3 months of 20 was equivalent to 1 month of 60 of total charge passed. So we could look at whether it was total charge or whether it had to do with the buildup of that charge over a period of time was more successful in providing any protection. So these are quite short-lived specimens, so obviously they have drawbacks from that, but it's to give us an idea of what we might expect. Here again, these specimens are sort of out, sort of being in a spray cabinet conditioned over that period of time. And what we saw with these by blotting are steel potentials. So this area at the beginning is what is happening with those potentials before we apply the cathodic protection. So you can see that actually generally they're drifting a little bit more positive as they're passivating after we've cast them, but a few of them we start to see them dropping. So some of them were starting to corrode, and most of our 3% specimens we felt were corroding, but most of our 0.5% specimens in these short-term trials had not been able to establish corrosion sufficiently at the time we applied the CP for the student who was doing this work. We can see here then we have the periods of the 1 month and the 3 months where we applied the cathodic protection. So where we're polarizing down to those protective values. Here they come up, and you can see here they come along, and then you can see points where we get these drops, where we can see that corrosion's been reinitiated. So in some cases we can see these fairly obviously. In other cases, even at the end of the trial, they were still drifting up, so that's suggesting that we were still maintaining protection in some of those specimens after the end of the application of the cathodic protection. So what we sort of did, sort of looking at these, and here we can see this in a little bit more sort of colour. So when we did the testing, we could see these are the criteria to determine if it's protected. And so we were finding that all the specimens were actually being protected by the cathodic protection when we tested them with their instant off, which is how you check for those. What we also saw, unsurprisingly, that the 0.5% specimens were giving bigger sort of decay values, so they were showing sort of better protection than our 3% specimens. We saw that a number of the specimens lost protection over a period of time, and thus we can see sort of those sort of where we've got sort of the 20 millivolts for the 1 month, we were getting sort of 10 days, but by the time we were going up to some of these larger ones, so the where we were getting sort of a 3 months at sort of 180 days, we were actually getting 55 days before we had any loss of protection. And indeed, the one where we went to 540 at the end of the 90-day trial, we still had protection sort of within them. So overall, sort of we saw that we were losing sort of like, there was no clear evidence of sort of like as to sort of what was actually happening as to causing that, but we were seeing residual protection in all of the bars for a period of time similar to what we'd actually seen on the actual structures and had been reported. So when it came to sort of the length of time and the amount of current passed, we saw no clear relationships based on these short-term trials, however, to be able to say that it was the time or the total current that was affording us sort of the better protection. So what we've also looked at are a number of structures, and we've looked now at 2 structures actually. I'll just talk about one of the structures here. So we've got a sort of a jetty, sort of here where we have a set of beams coming out. So there's the jetty, this is the side, this is what we've got. We've got a fender beam here, we've got sort of the deck, and we've got the top beam here, and then we have sort of pile supports. So we've been looking at the beams so within this, and these beams running down the length of that jetty. And that gives you an idea. So this is the jetty. So with this, so we've been looking at these beams that are in particular coming along the jetty, and that jetty has been going sort of out. So we've got one end that is near sort of as well as it's coming sideways. At one end, we've got the land there, and at the other end, it's more exposed to the ocean. This was a sort of mesh anodes, and we had 42 silver chloride electrodes, reference electrodes, we could monitor them. And we've got some ribbon anode in there as well. What we would look at from our criteria is this minus 150 millivolts is what's seen as the absolute passive criteria, that they should be more positive than this to be seen as maintaining their passivity. However, what we also looked at is whether they were getting near to this minus 150, but also if they were maintaining a positive trend and they weren't actually starting to fall back down. So even if they hadn't reached the minus 150, whether they were near it and maintaining it, to say that we felt they were still in a passive state, even though that was not what is specified in the international standard. But this we felt is indicative that they are still maintaining it, because if they're going to start corroding, we would expect the potentials to start to drop again. So this would be sort of thing that we would see. So we can see here, here's our minus 150, and this was in sort of D9 beam. And so it goes up, and while it moves around a little bit over time, you can see here it's still well above the minus 150, and there's no indication that this is really starting to sort of like drift back down for any indication that corrosion is occurring. This is another one sort of what we've sort of looked at. You can see here there are some ups and downs. These may be due to sort of tidal action or environmental effects, but overall you can see that it's still really in an overall drifting up that potential, and the potential's there, you know, very positive. So this would be very indicative that we do get residual protection in our structure. Here, however, is the sort of thing where we would say we've lost our residual protection. And you can see here, it moves up, and then for a period of time, it's still maintaining that. So this is where we would say it's near passive. It's not managed to achieve the minus 150, but it's been drifting up, and it's been happily really maintaining that upward drift. And then we suddenly get this drop, and it's dropped back down to a lot lower potential again. And this would indicate where we've lost that residual protection. So we think we've maintained the residual protection when we've switched off at this point for a period of time, but in this beam, which is D41, we've actually lost that protection over a period of time. So we're saying we've not achieved the minus 150, so it doesn't say it in what the standard would say, but we are saying we think we're still maintaining passivity here, and then we lose it. So here is one that's a little bit more difficult to see, but that again, it's showing you a close-up of what's happening sort of within sort of that system. And overall, when we looked at all of these beams, we saw that we had a small number that sort of didn't achieve passivity, but the majority either achieved this absolute passivity or would achieve sort of absolute based on that potential decay. So we can see here that only the black ones didn't achieve any residual protection at all. So you can see the majority of them actually reached our absolute passive for a period of time. And some of them, like you saw below on the previous slides, would achieve it based on that decay potential. So most of them would suggest that you will get residual protection. But why do we get some that don't? and why do we get some that fail after a period of time? So this was, we looked at the elements, and we could look at sort of the beams, the deck, the front beam, the back deck, and the back deck wall, and the fender beams when we looked at overall. And we can see it was distributed fairly evenly amongst those elements. So this is the total amount of elements that we looked at for each of those. So the elements that we were able to look at, 36 were beam. Out of sort of the elements that actually showed residual protection, slightly more of the beam showed residual protection than the deck did. But overall, they were nothing much other than the fact that the back deck failed and didn't show any protection at all. The other thing that we noticed is along the length of it. And so this would be sort of the more landward side of the structure. So the land is here, and this would be the more exposed to the tidal action at the end, because this is where going out to the end of the dock, starting to go out of the harbour towards the edge of the harbour. And you can see here, these are where we saw most of our failures. And this would suggest in the more environmentally exposed, the more aggressive regions, that we lose that protection very quickly, or we don't even see it. And so it does seem to be in those aggressive environments, we don't see that residual protection. And so that is something that would suggest, we think, if we've got sheltered zones, and this again might be the sort of thing where we see, say, de-icing salts, even though this is in marine environments, it might be analogous with that. We can expect to see residual protection. But in those very aggressive zones, we struggle to maintain residual protection or see it at all. And again, this would suggest in the sheltered zones where it's not an aggressive environment, we may possibly be able to use that hybrid system well, but it does perhaps raise a couple of questions when we're in these very aggressive zones, how long or how well that hybrid system with the residual zinc is able to protect it. And again, these are areas that we're going to go forward to look about on the rehabilitation of those structures and the residual protections. So I said, out of that, we were able to see the majority of the elements had some form of ongoing passivity, which is presumably coming from those secondary effects from that cathodic protection. So it's sort of both sort of the passive environment due to the CP and those secondary effects. It was in the less exposed environment, but it didn't really run specifically across the types of elements, other than that one type of that back wall element for some reason was not being protected, and that is perhaps because the tide just comes in and is always hitting that back wall continually, and it may be a very aggressive environment that it's always having the tide splashing against that back wall, and perhaps that is why we weren't seeing any residual protection there within it, which again would suggest it's very much about those aggressive environments. So that again is sort of things that we saw. It increases with current density, and so the bigger the current density that we can put in it, obviously the longer it will protect. So that would suggest the longer that we've had it on, the more protection sort of that you could expect from it. Was the main, so these are the conclusions from the sort of the first one. And again, sort of that was evident, but there was no direct relationship between the total charge passed and the residual protection. That slide should have been earlier, I'm afraid. So that's sort of the talk. Hopefully that's been sort of helpful, and sort of everyone has sort of learned from that. So thanks a lot to everyone. And if there are any questions, happy to answer them.
Thank you very much, Dr. David Lowe. So may I invite our Mr. Nandana, Engineer Nandana Amunuthuduwa, General Manager, INSEE Concrete and Industrial Sales of INSEE Cement, to conduct the Q&A session. Engineer Nandana, over to you.
Thank you, Dishan. Thank you, Doctor, for giving this informative lecture on the corrosion. So before we go into the Q&A session, I would like to invite Professor Nanakara. Professor Nanakara is with us throughout the session. So Professor Nanakara is the most recognized researcher and from the academia who is doing research on this concrete durability. So, Professor, do you have anything to add or comment on this presentation on, especially because being a coastal country, we are also having these issues. I'm sure you may have some experience to share with this forum.
I hope you can hear me. Is that
yes, sir?
Yeah.
Yes, can hear.
Okay. Yes, I mean, it's a very good presentation covering the durability of concrete and the chloride penetration. Now, we have, the corrosion problem in Sri Lanka, especially in the coastal region, mainly due to the, of course, so the chloride intrusion. On top of that one, it is the quality of the concrete that that we are using, because as you all know that if the quality of concrete is poor, especially the permeability is poor, very high, then the chloride penetration is very high. So that can easily penetrate into the concrete and promote the corrosion. Now, I would like to ask from the Dr. Lu, now how to evaluate the durability resistance or durability against the chloride attack of newly placed concrete, or when you do the mix design, how to evaluate the chloride penetration resistance of concrete. Now I'm just referring to the RCPT, is now very popular and all are specifying the RCPT test and also some values in most of the contract documents. So what do you think about the RCPT in evaluating the durability of concrete with respect to chloride penetration?
Yes, we do those tests here. I think it can be a very useful tool. I think my experience would be the different types of mix design can have different scales. So if you are using a fly ash mix or a slag mix or a general purpose OPC mix, you need to be slightly careful that you don't necessarily just look at them all on one scale, but you take into account what your mix is for what that should mean with regard to your chloride resistance. Because obviously in those tests, the chloride ions are not necessarily the ions that are being transported in the test. And also you've got your slag and your fly ash may well hydrate more slowly, and so they will improve over time. So if you're doing that as a 28-day test, that will probably be more beneficial for an OPC general purpose than it would be a 65% slag material. But over the course of the lifetime of your structure, your 65% slag, for example, would be a lot better and more durable than your 100% OPC test. So those, I would say, are what you need to be particularly careful of when you're using the RCPT, say at the 28-day test. But as a test itself, I think it's a very useful indicator of the performance against chloride ingress, and reuse the test. And I'm actually on a committee for geopolymer concretes, and we're trying to modify that test with a lower voltage to actually be able to apply that with geopolymer concretes as well, to understand it, to be able to use that as a the test. If you're, again, if it's a standard mix, you should also hopefully be able to perhaps do some 90-day ponding test data for that established mix as well, that can supplement your RCPT test to give you more information as well on what your chloride diffusion coefficients are going to be. And when you're doing your modeling as well, you want to think about the time factor as to how the time factor will change your chloride diffusion coefficient over the period of your structure. And I think most of the models that are now there will have time factors for OPC, fly ash, slag, with microsilica additions as well, that you can put into the model to see how your chloride diffusion coefficients change over time, and how you can design to try and get the lifetime by not just using the one data point that you get from your 28-day RCP test.
Yes, thank you, Doctor. No, I mean, just to add one more thing to that question. Now, what do you think about if you test RCPT value for fly ash blended cement or concrete with fly ash? Will that give the misleading result because of the chloride binding effect?
Well, yeah, that again can be an issue within them, that when you've got there, that's what I was saying about you have that problem, obviously, that you've got the very small time period. So you're not really going to be measuring much in the way of chloride binding within the RCPT test. And that's why I think it's very important to understand the material that you're dealing with and get the scale of values for that type of material to understand what that means. So if you've got a fly ash, for example, you want to be able to correlate that with other fly ashes for the value it gives you, rather than a general purpose OPC mix, which will give you a different value. Hopefully as well, the age factor will take into account the binding that occurs in those materials over the lifetime of the structure. But I would certainly say I don't think you should just use a single scale for the RCPT values for every single material you test. You need to understand the material you're testing and how it works, whether it is going to have a high binding capacity, whether it's going to have a longer hydration period when you're doing that test.
Okay, thank you very much for your explanation regarding that matter. Thank you.
Nandana, if I can just...
Yes. Thank you, Professor, for adding your thoughts to this subject. And Dr. we have another question from the audience. It says, in case of a slightly spoiled concrete element due to corrosion, is it possible to stop further corrosion simply by just preventing the access of oxygen and water, say by epoxy resin repair, or satisfy only with the epoxy repair?
Yes. If you can stop oxygen moisture, then yes. I mean, the applications of silanes, for example, is something that has been applied, particularly where you have de-icing salts, to stop the moisture getting in. And that has been pretty successful in stopping corrosion. Barrier coatings, again, you can use those with epoxies. They can at times be quite expensive to cover an entire structure with an epoxy. And obviously, if it fails, then you've got an area that may become more of an anode. If you're getting one area where you can start to get access for moisture, for example. So you have to be a little bit careful with applying the barrier coats, that you maintain those barrier coats and have them over the whole structure within it. But yeah, but certainly, I think in the UK, they just mandated to put silanes on all motorway bridges about 20 years ago, and that has certainly been beneficial within it. Sometimes in the marine environment, you also have the problem, if you want to apply any of these barrier coatings, that they struggle to adhere in the sort of when you've got sort of a lot of moisture in the area anyway. So again, that can be a problem sometimes with applying the coatings to your structure, that they never really get good bond, because in a tidal zone or in the spray splash zone, they're getting wet so often that they're perhaps sort of their performance isn't as good. But yeah, certainly removing any of the moisture is a good way to go to stop corrosion. Your mic's off.
Sorry. So we'll take another one question from the audience. It is, dear sir, what is the precautions that we can take to reduce the corrosion before and while doing the constructions?
Yes, well, I would say that's my experience would be 75% of the structures I see with problems are because they weren't built how they were supposed to be. So I think there are a number of things that you can do with that. The first is in the design itself and making sure that you get a good design for your concrete and understanding the cover that you need to specify for that mixed design. And that's what I was talking about a little bit about. You can work out sort of both the chloride diffusion coefficient or characteristic that you want of your concrete, and then use that with your cover depth to model it to ensure that you get the residual lifetime. Then when it comes to doing the construction, I would say make sure that you get the specified cover. And certainly now in Australia, and certainly in quite a bit of Europe, cover surveys have to be done by the contractor once it's built, and it's in them on the contract, if they've not achieved the cover, to go back and achieve the cover. And by having that in the contract that they have to do the test and they have to pay for if it doesn't, has made a dramatic improvement in the amount of that cover is generally achieved. And that, I think, is one of the main things that I would say you can do as a relatively straightforward thing. With someone comes with a cover meter at the end of it and just does readings and see that it's the cover that's specified. And that's pretty quick to do. You don't have to take any cores to see the strength. You don't have to go away and do any RCPT on what's being cast on those cores. You've just got a man and a cover meter checking that the design cover has been achieved with it. Obviously, you do need to ensure, I would say as well, that the quality of the concrete by having sort of testing of the strength of the concretes to ensure that they are the right concretes that you're putting into it. But you also, things like the design, to make sure that you've not got too much steel in there. And so you're going to get honeycombing because it can't actually compact into your element. And you sometimes get that, particularly, I think, in piles, that you get just too much steel occasionally in them and you just don't get compaction in some of those piers. And so you have honeycombing in them. So again, that's something to look at within the design stage, but also when you're doing the construction, to make sure that it is vibrated and that you have got the compaction you expect. And the final thing, and again, particularly in hot countries, is to ensure that it's properly cured, that you don't decide that it's too much trouble at the end of the day to put on the curing membrane or the plastic or the hessian and you leave it and you come back the next day. And I have plenty of examples from Australia where Friday afternoon syndrome has come in and it's been a hot and windy weekend. They come back and they've got lots of cracking in the concrete because it hasn't cured properly over that period of time. And then it's very difficult to rectify that. And you've lost some of the effective cover because of it's been badly cured. And that, again, I think goes back to that QA and just making sure that that's sort of done in the construction process. So all of that comes into it. The final thing I find when I used to work in industry is that doing the durability assessment of their design would come right at the end. And if you said you've got a big problem, you would generally be told to try and find a way around it because we weren't going to redesign it at this point. And they may even have started some of the construction. And so getting sort of the durability people involved in the earlier design stage can, again, be very beneficial to making sure that you get the durability over the time period. But specifically in the construction stage, I would say making sure you've got the cover there and making sure you properly cure the concrete when you've actually cast it are the two main things you can do on site to make sure you've got good quality concrete.
Okay, thank you, Dr. Lee. There's another question saying fly ash, slag or composite cement, which one is more suitable in marine environment and why?
They can both be useful in marine environments. I would say probably the fly ash is slightly better. And I think part of that is that the shape of the fly ash also means it works as a bit of a pore blocker as well as the supplementary cementitious material. But both of them are better than using sort of standard OPC concrete. And they will both give better performance. They will generally both have higher binding capacities. And over the lifetime of that structure, they will achieve a lower porosity and a lower chloride diffusion coefficient, so lower chloride ingress. So I would say 30% fly ash or a 35% slag are both good mixes to use in marine environments. But a bit is the availability as well of what you've got available, particularly in Sri Lanka, as to the availability and cost may be a big factor for yourselves.
Yes, thanks, Dr. I think Dr. Musa also has to add something here. So Musa is our head of production solution development. So Musa, any things to be added from your side?
No, I mean, I would like to say thank you so much, Dr. David Lowe. It was very somehow passionate presentation about mechanisms of deterioration regarding corrosion. When we look in general, you know, you have presented at the very beginning how important the impact of concrete corrosion as a social cost. That is really show the importance. And if you look also to even concrete standards, if I take ISTN or EN, out of the 5 exposure conditions, 4 are related to corrosion. Seawater, de-icing salt, carbonation. We can find this is really a key concrete deterioration somehow that can impact. Now, if we look back, for example, you show the bridge of Genoa, the Morandi Bridge. This was built when we have checked recently, we checked the concrete quality. This bridge did not collapse because it failed the compressive strength. The strength of the concrete was good, was not really the problem, but the corrosion happened because it was exposed to marine structure. The Genoa is in the Mediterranean Sea. Therefore, the wrong cement was used because there were not enough aluminate to form calcium chloroaluminate and densify, as you mentioned it very well, the porosity over the time. Therefore, corrosion happened and we have this drama. Okay. Now, I want to come back to Sri Lanka because in Sri Lanka, very often, when it comes to durability, is we talk about durability like a question of megapascal very often. And second, we miss some, I could say, some indicators to be more subjective, to be moving from something we say is durable or let's say it is objectively, we talk about, like Professor Nanayakara mentioned, the RCPT test. When I come to Europe, for example, they will talk about the Nordic test. Today, you have a lot of use of the ResiPod, the resistivity test. Okay, now, with your experience, if I look to Sri Lanka, okay, what would be for you an easy test? Because we know the RCPT test, it is a little bit known internationally, it is used in a lot of big projects. What you could recommend for engineers for the construction industry in Sri Lanka, a simple test that we can somehow perform to have an idea about the mix design. If this mix design from the very beginning could have a good resistance to corrosion over time.
Yes. I mean, as I said, I think the RCP test is a good test if you have the equipment there, because it can be done over a relatively short period of time. So the Nord test, I think, again, is 90 days to run those. Mm-hmm. They are good when you've got standard mix designs, to have that data as well, to be able to back that up, to be able to do those, to ensure that with that test, you've got more information because it runs for a longer period of time and the concrete is older. I think one of the issues with a lot of these tests is that you're doing it on a relatively small batch of very good concrete. Because it's made specifically for that test rather than made to go in the structure. And it tends to be, in particular, better cured and better controlled. And that, I think, is one of the biggest issues, is that whenever you're doing these tests, you've got what we might call labcrete that's invariably better than sitecrete. And that is where the issues, I think, tend to arise. This, I think, is where having the ability to actually do the cover tests is good, that should ensure that you've got the cover on the real structure. And I think that is probably sort of more important to a degree, as long as you've got someone who is, if you've got a good design, which hopefully you will have, making sure that that design then is what is sort of put on the structure is important for it, I would say. But yeah, I would say that the RCP test is a good test. You can do the resistivity test as well within it. Again, that can be relatively straightforward, where you're just sort of testing the resistivity. I find that practically more difficult to get right than the RCP test at times, actually, just from my experience of running that and getting a good contact with the for the resistivity meter. I feel sometimes that I am getting too high a resistivity for the material. I would say is my practical experience of that at times. And so while it can be a good test, I find it's probably easier to get wrong than the RCP test. But doing them both is good and getting that complementary information. What I would say is, don't just rely on one test. You would like to do 2 or 3 of them to be able to look at it. Again, the resistivity test you can do at 28 days and the same time as the RCP test. And we usually do it on the same course. So we will cast a few cylinders and we'll test them all for resistivity, and then we'll probably cut them and do sort of 2 or 4 cores slices for the RCPT out of the cylinders that we've taken for it, is what we tend to do when we're doing sort of the lab trials of those.
Thank you very much, Dr. David. I think this session today is a very interesting session. I can see that a lot of questions, queries are coming to get it forward to the panel members, including the presenter. But considering the time limitations, especially I think Dr. David's time is very late night, I guess. So we would like to go to the next item. So thank you very much, Nandana, Engineer Nandana Amunutudua. He is our General Manager of INSI Concrete and Industrial Sales. So at the same time, I would like to thank Dr. Chandan and Dr. Shamila for the coordination of this resource person. And let me invite Dr. Moza Balbaki, Head of Product and Solution Portfolio of INSI Cement, our resource, another very vital resource person to our fraternity in Sri Lanka. Dr. Moza, over to you to give the vote of thanks.
Okay, thank you so much, Dishan. Let me start thanking really everyone who attended this very interesting knowledge sharing session about durability, corrosion, and rehabilitation of reinforced concrete. Of course, I know that we are still not able to, to meet together, as we did it in the past in our premises at Periagoda, at our innovation to industry collaboration space. But I hope that soon, very soon, we'll be able, that the pandemic will be somehow behind us and that we can meet again, have a physical contact and somehow talk more in deep on our relation. Having said that, really on behalf of INSE, I would like to express my gratitude for the outstanding presentation, really outstanding presentation and contribution from our guest speaker, Dr. David Lowe. Thank you so much, Dr. David Lowe. I know I'm looking just now to the time in Melbourne, it's almost midnight. Thank you for your commitment. Really, it is very, very somehow great for us to have you in this knowledge sharing session, to have your opinion. Australia is an island, Sri Lanka is an island also. Therefore, we have learned a lot from your presentation. Thank you so much. Really, we are very grateful for that. I would like also to really take this opportunity to thank our friend, Dr. Chamila Gunasekara, for his coordination, facilitation. We are working together with Dr. Shamila, Dr. David Lowe on a PhD program with MIT. And thank you so much, Dr. Shamila, for showing up also. Therefore, I would like to say I don't want to take more time. I want also to thank Professor Nanayakara for his also intervention. And I think that this is great to have in Sri Lanka also such a resources. Because Sri Lanka today is a country where we have a lot of infrastructure project, large infrastructure project where corrosion is important. And we are very grateful for these resources. Therefore, we will somehow continue to facilitate our monthly knowledge sharing session online because we have a special somehow situation today with Corona. This is really to ensure the health and safety of our stakeholders. And we really look forward to hosting you at our INSE collaboration space once again till I hope that we continue to stay all safe, all of us. And thank you again to Dr. David Lowe for his presentation and for all participants who really attend to this knowledge sharing session. Thank you so much and see you next, webinar knowledge sharing session, the last Thursday of next month. Thank you so much and have a nice evening, everybody. Bye-bye.
Thank you very much, Dr. Moza, for your kind thoughts and inputs and also the word of thanks. So let me thank again Dr. David Lowe, Senior Lecturer, School of Engineering, Melbourne City Campus, RMIT University, for the session today, Durability, Corrosion and Rehabilitation of Reinforced Concrete. Ladies and gentlemen, make sure in month of May 2021, please join with us with our 11th webinar session and the 26th knowledge sharing session by Innovation to Industry, Eye to Eye, INSE Eye to Eye collaboration space. Until that, be safe and have a a healthier life. Thank you, ladies and gentlemen. Thanks again, and have a good night.
Thank you. Bye-bye.
Thank you very
Thanks
much,
a lot.
everyone.
Good night.
Thank you.
Thank you.
Thank you.
Hopefully make it to Sri Lanka for the next England cricket tour.
Yes, really. Yes.
We loved welcome you, sir.
Yes. We will
Yes.
make
Let's
it
get-
happen. Thank
Let's
you.
get up then. Thank you very
Yes.
much.
Thank you so much. Bye-bye.
Thank you.
Bye.
Thank you so much.